Okay. Okay, I think we can start.
Okay, so you have about 45 minutes for your talk, okay? And then yeah, we will start with a question from the jury. So when you want.
Okay. So hello everyone, welcome to my PhD thesis, which is about whole body teleoperation of human robots. So let's get started. So every year, the use of robots in our society is gradually increasing, and in the production lines of manufacturing settings, the presence of industrial robots has now become a standard. And since they have to perform predefined tasks in well-known environments, they have the simplest structure that allows them to accomplish their given task efficiently. And they often have the shape of robotic arms. However, there are situations in the real world that involve some creative adaptation of motion and the way the task is performed. For example, operations in remote places like a space station or an oil platform very often requires performing the task in unexpected ways. And similarly, disasters are events that are by definition out of the ordinary routine, and during which robots could be used to save human lives if they can adapt to the highly dynamical uncertainty of the site. And the Fukushima nuclear accident in 2011, we saw that humans tried their best to go in, trying to mitigate the disaster so that it would not be as bad. The problem was that the radiation levels were too high, so they had to turn around before they could open the valves to vent the radiators. So robots that can go wherever they need to, regardless of how bad the contamination is and how difficult the environment is to navigate, will be able to spare many human lives. And human robots will be the perfect candidate because they have the potential of being as versatile as human beings. And differently from other robotic structures, they have a kinematic robotic platforms that have a kinematic structures that allows them to enter narrow spaces, navigate confined and cluttered environments. And their anthropomorphism also allows them to operate well in environments that were primarily designed for humans. They can perform by manipulation. They can bend to pick up objects from the ground, reach high places by the ceiling. They can also crawl, push objects aside, and walk on uneven terrains and climb stairs. So having a complex body structure, they are difficult to control autonomously, especially in those situations involving interaction with the environment and other human interactors. And the dynamical uncertainty of these situations presents critical challenges to the robot cognition system, which despite recent progress based on machine learning techniques cannot produce physically and socially competent robot behaviors in all situations. So a promising solution is to combine the human and the robot capabilities to solve complex problems remotely. And by using the robot as a human avatar, the high-level decisions and cognitive skills of the humans are fully exploited and transferred into the robot. And this technique is referred to as teleoperation. And human-robot teleoperation started to become an important topic in the robotics community, especially after the DARPA Robotics Challenge, a prize competition held from 2012 to 2015, during which the teams were teleoperating human and robots using classical interfaces consisting of a mouse, keyboard, and display, performing search and rescue, possible search and rescue tasks. And after the competition, this high-level teleoperation is also being proposed for bomb disposal applications, where the user can guide the footstep planning of the robot and the fetters during the different manipulation phases. And the operation requires some time due to the manual selection of the inputs and corresponding generation of the outputs. So an alternative is another possibility is to use to exploit the human-like morphology of human robots and let them replicate the whole body motion of the human captured by a motion tracking system. And this, combined with the intelligence of the human operator, makes the robots realize tasks fluently as human avatars. And the whole body motion of the robot can be controlled precisely, while the human wearing a virtual reality headset can feel as they've been projected to the remote situation. And it's right after the huge growth of this virtual reality technology that the concept of teleoperation, conceived as remote control of robots in dangerous situations, started to extend to the concept of teleexistence. And in this case, the focus is more on virtual existence, existing in the remote location, feeling virtually present, and experiencing all sensations from the remote side. And Susumu Taki came up with this concept, envisioning a future society more time efficient and ecological, where one, while staying at home, can visit a space station, visit patients at the hospital, visiting family in another country, or attend conferences overseas while interacting with the remote environment. And also in this case, humanoid robots would be the perfect candidate, since they can maximize the sense of embodiment of the user into the robot. And the robot is more likely to be accepted by other human interactors at the robot side, since the actions of the robot are more legible, and also the interaction can be enriched by expressions and gestures that are more human-like. So now that we've seen the general context, we can see the generic architecture of a complete teleoperation system. First, the user motion and other quantities at the user side are measured. Here we focus on the motion. So the user motion can be captured by using optical tracking systems consisting of several cameras and retroreflective markers, or by recording to inertial-based technology using IMUs, or even exoskeleton, which can be dual-arm exoskeletons or whole-body exoskeleton cockpits. And in this case, the system is set to be bilateral because the exoskeleton is both used as an input, as the input that generates the robot motion, but also as feedback to get the feedback from the robot. So once the human motion has been measured, then it's translated into an equivalent one for the robot. And this translation is referred to as retargeting. Then the resulting trajectories can be modified by using some robots assistance, for example, by compensating for the delays or by using share control approaches. And these approaches use some robot autonomy to improve the efficiency of the user teleoperating the robot. In fact, there are certain tasks that might be difficult to perform, where low errors in motion inputs lead to large errors in motion outputs, and where some assistance from the robot can help the user achieve that task. For example, by keeping a fixed translation and rotational offset between the end effectors while moving an object around. Then the resulting trajectories are set as references for the robot controller, which computes the low-level commands for the robot, the joints positions or joint torques. And then the state of the robot and the state of the environment are measured and transmitted as feedback to the user. And the state and the environment state can be measured and transmitted as they are. For example, the sound recorded from the environment of the robot, or they can be translated, mapped to a different feedback for the human. For example, the forces acting on the robot can be translated into vibrational signals used to actuate a vibrotactile belt that can give a sense of the robot's balance to the user. And so share control approaches can also be used in this translation retargeting of the feedback. For example, haptic feedback can be used to guide the user towards certain object locations or toward more comfortable postures. So encircled in reds are all the components that I have implemented during my thesis. First, we measured the human motion. Then we translated into an equivalent one for the robot. We use some robots assistance to compensate for the delays. And then the resulting trajectories are tracked by a whole body controller that makes the robot move accordingly. And as feedback, we streamed the images from the robot's cameras and other external cameras. So these components, I implemented these components to tackle three main challenges related to the whole body teleoperation of humanoid robots. So a first challenge is to the so-called motion retargeting problem, which consists in transferring the human motion to the robot so that the robot moves in a human-like way. Yeah, okay. So there was someone with the microphone on. So to check transferring the human motion to the robot so that the robot moves in a human-like way despite the differences in the body structure, which can be a different height, a different length of the limbs, a different joint range, and differences in the dynamics, which can be a different center of mass location or in general a different distribution of weight in the different body parts. And then one should find a controller that allows the robot to follow efficiently the human references while achieving the robot's balance. And in teleoperation, we also want this controller to be as generic as possible because we don't know exactly what kind of tasks we will have to perform. And there's also the problem that the testing of the controller is usually done in simulation, and working solutions in simulations often cannot be transferred intuitively to the real system. Another challenge is to be able to teleoperate the robot while compensating for the delays in the network. This can get pretty significant, especially in space applications. For example, in the Metron project, where a robot on Earth has been teleoperated from the ISS, typical delays were around 0.8 seconds with a maximum of 3 seconds. So in the rest of the presentation, I'm going to present the solutions to these challenges that I proposed during my thesis. First, we'll see how to transfer the human motion to the robot, then how to learn optimal controllers that make the robot move accordingly, and then how to teleoperate the robot while compensating for the delays in the network. So, okay, so the whole body motion of the human can be represented by several trajectories of different body parts. And the goal of motion retargeting is to produce equivalent trajectories for the robot. And the choice of the selected trajectories is usually standard. The center of mass position is used to encode the balance of the robot. The pose of the hands on the feet are necessary to perform any manipulation or locomotion. And the orientation of a specific link, like the head, the chest, or the floating base, is usually included to provide more stability to the robot. And the joint angles trajectories are used to achieve some human-like motion. So once the robot trajectories have been specified, then we need a controller that makes the robot move accordingly. So let's start with the generation of the robot trajectories. The first step is to capture the human motion. And in our case, we use the DXN system consisting of a Lycra suit with 17 wired MUs. The system captures the movement of the user, generating as output a 3D model of the human skeleton, and streaming the pose of the tracked body segments, the center of mass position, and joint angles. And all this information can be mapped to the robot. As for the sometimes it's very slow. Okay. As for the joint angles, the DXN skeleton has 66 degrees of freedom, corresponding to 22 spherical joints. So after several testing in simulation, we identified the mapping between each spherical joint and its axis of rotation and the corresponding joint of the robot. And we considered the variation of the posture of the human with respect to the starting posture to compute the instantaneous joint angles of the robot. For transferring the translational movements of a body segments, we use a fixed scaling factor. And for rotational motions, we used an identity map. to transfer the human center of mass, we consider the ground projection of the center of mass of the human on the ground. And then its position with respect to an arbitrary foot is projected onto the line connecting the 2 feet. And this value is normalized to obtain an offset compressed between 0 and 1. So when the human is in a symmetric pose, the offset is value around 0.5. And when the center of mass is above 1 foot, the offset is value either 0 or 1, depending on the foot. And then from this offset value, we can reconstruct the center of mass position of the robot on the line connecting the 2 feet. And if we apply the same approach also on the line orthogonal to the feet line, we can reconstruct the complete 2D ground projection of the center of mass of the robot. And so, yeah, the retargeting formulation of the center of mass is conceived to imitate the human behavior as much as possible. But due to the different dynamics of the robot of the human, a similar center of mass position doesn't ensure the balance of the control robot. So to ensure the balance of the robot, we need to use some stability criteria. And a common solution is to rely on the concept of the zero moment point, which is the point at which the forces generated by gravity and inertial forces, the tipping moment generated by gravity and inertial forces is 0. If this point is kept at all times inside the support polygon, then balance is guaranteed. So we, by employing the dynamic equation of a simplified humanoid model, the linear inverted pendulum, we set up an optimization problem that provides a minimal correction of the center of mass at each controlled step, so that the zero moment point of this linear inverted pendulum stays inside the support polygon. So we now defined all the trajectories from the human, and then we need a control that makes the robot move accordingly. And since we have many tasks, many trajectories, many tasks to track, a common solution is to use a multitask QP controller. For a given task, the quadratic program formulation consists in solving the following optimization problem, where U is the control input, A is the equivalent Jacobian matrix of the task, B the reference value for the task, the second term is a regularization factor, and then we have equalities and inequalities constraints, among which we have the control input limits. And usually, since we have many tasks, these are organized, are given different importance, different priority, and we can specify different types of priorities. Soft priorities are simply weighted relationships, and strict priorities, which mean that a task in a lower priority acts in the null space of a task at a higher priority. So the multitask QP formulation has become widespread in the literature, not only because it allows one to specify multiple tasks, but also because it can be applied to different types of control. For example, depending on the nature of the control input and the way the references are specified, we can implement inverse dynamics control, momentum-based control, inverse kinematics control. And the use of multitask QP controller clearly is not the only solutions. It's also possible to record to a whole body model predictive controller, to a full state linear quadratic regulator, or to a contact force distribution optimization, although these approaches are less common because they're more complicated. Yeah. So we opted for an inverse kinematics-based QP controller. As task, we considered the posture of the neck, of the torso, and of the arms. And then we also considered the pose of the feet. Then in this work, I had to maintain contact with the ground, since we consider only double support motions. And we also additionally considered the center of mass ground projection and the orientation and the height of the floating base. So here is a video of the experiment where an operator wearing the motion capture suit is controlling the robot ICAB. And we decided to use an inverse kinematics controller because it's easiest to debug and is the one that we needed to find a mapping between the posture of the human and the robot. And in this case, the posture of the legs was not retargeted directly, but indirectly through the center of mass and the floating base tasks. And here we can see that even if the user generates some motions that is unbalanced for the robot, the robot keeps the balance, thanks to the center of mass correction that keeps the zero moment point inside the support polygon. So I also collaborated with ICE in the context of the JSPS fellowship, and we implemented the same retargeted approach in the HRP4C robot, but this time using a task space inverse dynamics QP controller. And in the constraints, we included the robot dynamics equation, the no sliding contact constraints, friction constraints, and auto collision constraints. And here's the resulting simulation. On the left, you can see the HRP4C robot. On the right, the corresponding exoskeleton from Xsense. And yeah, unfortunately, only simulation because I couldn't go to Japan. I couldn't try anything on the real robot due to the pandemic restrictions. So yeah, only in simulation. In this case, we could also retarget the posture of the legs because of the inclusion of the contact constraints. And this makes the robot move in a much more human-like way, but also the inverse dynamics approach helps. The posture of the legs is important because especially the hip joints are responsible for the motion of the legs, but also of the trunk whenever the contact with the grounds are maintained. Then we tried also to retarget the footsteps from the human. And we saw that it's not a good idea because the stride of the robot is typically shorter than the operators, and the humans cannot walk as fast as humans. So this was leading the user to walk in a very unnatural way. So we decided to use a higher level teleoperation mode, where the user can use a joystick to give high-level directions, reference velocities for a MPC gate generator, which computes the center of mass trajectory and the footstep locations for the robot. And we collaborated with the University La Sapienza Rome and integrated their MPC into our framework, teleoperation framework. So here's the user that was wearing a virtual reality headset connected to the robot's cameras and using a joystick to guide the walking of the robot. On the top left, we have the images from the robot's cameras, and the user is guiding the robot toward the box. The user can decide if teleoperating the robot with this high-level teleoperation, but can also switch back to having the full control of the robot. Or it can also decide to replay some pre-recorded motions. In this case, the user presses a button to make the robot space the legs. And you can also, press a button to take the full control of the robot, in this case, to pick up the box from the ground. And here we can see the robot is pretty stiff while trying to pick up the box from the ground. And this was because the parameters of the controllers were not optimal, and we'll see this in the next part. So I implemented the same system also for the HRP4C robot, and using the task space inverse dynamics QP controller. And here we can see some alternation of walking motions guided by PS4 controller, and some and the whole body motions teleoperated from a pre-recorded Xsense sequence. So let's get to the part concerning the controller. How can we get a control that is optimal? Here you can see another video of the HRP4C robot. And in this case, we have also the Cartesian tasks for the end effector. So the orientation of the head, if we want images from the robot's cameras that are more stable, and also the pose of the hands if we want to be more precise during manipulation. We can see that the robot, in this case, was struggling to keep up with the speed of the references from the human. And this is because we need to tune these parameters that are decide how the task error converges to 0. However, if we try to increase simply these weights, we might get a behavior like this one, where the controller fails, the QP fails, and the robot falls. We see that the robot is trying to track instantaneously the hand trajectory, and this makes the QP fail. So more in general, we need to tune also other parameters, not only the feedback gains, but also task priorities. There's also the problem that working solutions in simulation might not work on the real robot. Here, for example, we can see that the robot in simulation was working, but then when we tried it on the real robot, the robot falls. So we have two problems. One problem is that tuning task priorities and gains is time consuming and requires the expertise of the human and many tests. And another problem is that working solutions in simulations do not necessarily work on the real robot. So we need a method to automatically tune the control parameters and to obtain a controller that gives with a good tracking performance. But also we want this controller to be as generic as possible, so that we don't need to rerun the optimization for each specific motion. And also because when we teleoperate the robot, we don't know the exact sequence of, a priori, the exact sequence of tasks that we have to perform. And for that, we proposed a multi-objective optimization approach. And many approaches have been proposed in the literature. And when both soft and strict priorities were learned, this was usually done for few tasks and in simulation. And there's the problem that when we control human robots, especially if you want to teleoperate them whole body, we have to control many tasks. And unlike robot manipulators, human robots have a very complex dynamics, which often leads to a big reality gap. So let's see why we should use a multi-objective optimization approach. Since we want a good tracking of the human references and also to achieve the balance on the robot, these two objectives might be conflicting. And a common solution is to optimize them simultaneously is to use an aggregated objective function. However, by doing so, we are weighting the different objectives, and we are implicitly encoding solution preferences. So the problem is that then the weight have to be chosen carefully, and if we don't choose them correctly, then we have to rerun another optimization, and this can be time costly. So a better solution is to use a Pareto-based multi-objective optimization approach. In this case, the result of the optimization is a Pareto front, which is a set of optimal trade-offs. It's a set of non-dominated solutions, and a solution x1 is set to dominate another solution x2 if it's better for all the objectives. If it's worse for at least one objective, then both solutions are equally interesting since they represent different trade-offs. So we considered, as I explained before, a multitask QP controller, and we consider a generic control structure. So we have both soft priorities and strict priorities, and we parameterize the strict priorities with real valued parameters that we call the level activators. We consider an inverse kinematics approach without losing generality. And in this case, as feedback gains, we had only the convergence gains, the proportional gains lambda. So here's the flowchart of the learning procedure. First, we have a training phase that is done offline in simulation. And then we have a testing phase that is performed online on the real robot. So during the training, the multi-objective optimization. Oh, battery. Sorry, the battery of the computer. Okay. During the training, the multi-objective optimization process based on rollouts performed in simulation computes a set of Pareto optimal solutions, and each solution represents a different control configuration, which satisfies different performance criteria. And these are optimized on a training sequence. So the first block of our method is the motion generator. In our case, we use the motion retargeting framework, but that I presented before, but any motion planning algorithm can be used. And as multi-objective optimizer, we use the NSGA tool, which is one of the most efficient stochastic multi-objective optimization algorithms. And as objectives, we consider the accumulated tracking error, and a robustness score that in this work, since we consider double supermotion, was the distance of the zero moment point from the center of the support polygon. And we wanted to minimize both objectives. So once the training phase is over, the result of the optimization is a Pareto front. From this Pareto front, the user can select some control configurations and try them on the real robot until they find a configuration that is satisfying. So here's an example of the Pareto front on the right. each point of this Pareto front corresponds to control configuration. So to certain values of the control parameters that we considered, then in our case was more than 20. On the bottom right, we have the most high-performing solution, which is also the least robust. And on the top left, we have the most robust and least high-performing solution. So this is the training sequence that we used. And we tried to simulate all the robots parts since we wanted to obtain a controller that was as generic as possible. So let's see how we can, once we have a Pareto front, how we can select a control configuration on the real robot. So clearly the most robust solution works in simulation, and as we would expect, also works on the real robot, but it's very poor in performance. So instead, the most high-performing solution clearly works in simulation because it was optimized in simulation. But when we tried it on the real robot, it could happen that the solution doesn't work, the robot falls. So we move progressively towards solutions that are less high-performing and more robust until we converge to a solution that achieves balance on the real robot. And this solution represents a valid trade-off between performance and robustness. And to show how a controller optimized with this approach can be used for generic motions not previously encountered in the training sequence, we teleoperated the robot while performing several tasks. In this case, the robot was opening the door while using a fingernail. Here, still opening the door, and then it's gonna close it back. In this work, we consider only double support motions. If we want to extend the approach also to other kinds of motion, clearly we need to use another robustness criteria. And with the same controller, we can also pick up the box. We can see a comparison with the previous controller, which was not optimized. And now the robot motion is much more fluid and human-like, and the controller is much more reactive. So we're gonna, for even going faster, even going faster, the robot keeps the balance. And here the user wanted to make the robot push the box aside, and with the same controller we can also perform some manipulation. Here, the robot had to push the ball in the box. The first attempt is a fail. The second one succeeded. And with the same controller, we can also have some hip-hop style dancing. Okay, so let's get to the last challenge, which is how to teleoperate the robot while compensating for the delays. And first, I wanted to show you how to what having delays in the network generally means. So the user also in this case controls the robot by means of the motion capture suit. And the virtual reality headset is connected to the robot's cameras and another external camera. And in this case, we had a delay of round trip delay around 1 second. This means that we have a delay from the user to the robot, and from the robot to the visual feedback the user receives. And we can see that by focusing on the head motion. First, the human moves the head, then the robot, and then the robot in the visual feedback. And this delayed feedback can get very confusing, especially during the crucial parts of the task execution, and it often makes the user fail. And the first studies with robot manipulators suggested that the typical user behavior is to adopt a move and wait strategy to avoid overcompensation of the delayed perceived error. However, further studies also show that this approach is not efficient, even for when the communication when the delay is around 0.3 seconds. So the compensation of the delays for the visual feedback in the literature is usually done by using predictive displays. And these are virtual displays representing a model of the robot and its environment. The user teleoperates the robot in this virtual environment, and then the same commands which will be delayed are sent to the real system. However, since there's going to always be a difference between the real and modeled environment, these systems only offer approximate cues until actual feedback is available, and they probably should be used as support tools rather than solutions on their own. So we introduce a novel teleoperation system in which the operator gets a synchronized video feed of real images from the robot. even when the communication channel imposes a 1 to 2 second delay. And each time step, the robot analyzes the data it has received so far, measures the communication time, and predicts what the user is most likely to do in the next few seconds. And this prediction makes it possible to make the robot move with enough anticipation so that the visual feedback that the user receives corresponds to the past of the robot, but to the present time of the operator. And for the prediction, we decided to rely on probabilistic movement primitives, which are a probabilistic model for representing a trajectory distribution. They model the time-varying mean and variance of the trajectories. And we decided to use this probabilistic representation because then we can apply probabilistic operations to the movement primitives, such as conditioning, which allows us to update the prediction based on the observations. Also to achieve generalization to novel situations. Here we can see an example. This is an example of the ProMP. So the gray lines are the training trajectories, and then the light red line is the learned mean trajectory of the ProMP, and the transparent region is the associated standard deviation. Then, if we consider a test trajectory, the dark red line, as we get some observations of this trajectory, the dashed black lines, we can update the prediction accordingly. In this case, we can see that the blue line is updated. And after getting enough observations, the prediction gets really close to the actual value. So let's see how we use the ProMPs to compensate for the delays. First, the user teleoperates the robot in a network without any delays, while performing several tasks, and for each task a ProMP is learned. So then we teleoperate the robot in a real network with delays. First, the user motion is recognized, which means that we associate the right ProMP to the correct motion. Then the exact speed at which the user is executing the motion is estimated, and the ProMPs are modulated accordingly. Then the ProMPs are the prediction is updated, and then is applied into the future so that the feedback the user receives correspond to what the user is doing. So we considered different whole body tasks, including reaching bottles at different locations, and picking up a box from different heights and placing the box at different locations. And for each task, we learned a ProMP for each of the control part of the robot. For learning the ProMPs, the steady trajectories are modulated to have the same duration. And for each demonstrations, the weights are simply computed with linear ridge regression. So for the motion recognition, we minimize the distance. We identify as the ProMP that better describes the current motion, the one that minimizes the distance between the first delayed observations and the mean of the ProMP. Then, to match as close as possible the exact speed at which the motion is being executed, we estimate the actual trajectory duration. During the learning step, for each ProMP, we record a set of time modulations. And from this set, we can estimate which one better fits the current motion, the current speed, by again minimizing the delayed observations with the predicted trajectory. Once the set of the ProMPs is recognized, then we can update the prediction by applying Bayes' theorem, as I showed before. And finally, we can apply the prediction in the future at the current time plus the forward delay, which can be measured exactly by comparing the time, the current time, the robot side with the time attached to the transmitted data, and the forward delay, which is given by the jitter buffer, a component of the video streaming system, which introduces an additional constant delay by reordering the packets. So initially, the teleoperation is delayed, since to produce the prediction we need some observations. And in this case, we have a round trip delay around 2 seconds. And we can see that by focusing on the head motion, first the user moves the head, then the robot moves the head, and then the robot in the visual feedback does. And so first the user moves, then as the robot gets some observation, it starts anticipating the operator's motion to synchronize the user comments with what they perceive. And we can see here that the robot will close the hands toward the box, will pick up the box before the user does. Once it does, it's synchronized with the user, then the user and the visual feedback are synchronized. So whenever we'll see the green box, we can just look at the visual feedback and the user, so not to get confused. We can see again the video without pausing. First, we get some delayed observation, then the robot starts anticipating the user motion, and the user motion and the visual feedback are synchronized. Now the robot will place the box back on the table. So we get some delayed observation. The robot anticipated drops the box before the user does, and the user and the visual feedback are synchronized. We can see also another experiment with a lower delay, around 1.5 seconds. Here again, the user starts moving, the robot picks up the box before the user does. The user and the visual feedback are synchronized. And now the robot will place the box on the container at its side. You can see now the feedback in the user. Okay. So here's the tracking error with respect to the non-delayed DIO trajectories, and for the right hand position. So the red one is the error that we get if we don't use any compensation, and we can see that the error is around 5 centimeters already for a 0.5 seconds delay, and it then increases significantly for a 2 seconds delay, reaching about 17 centimeters. 2 seconds delay, yeah, 17 centimeters of error, and for a 4 seconds delay to 30 centimeters of error. The compensated the tracking error of the compensated trajectory is much better. So the green one is the error if we consider the synchronization phase, and the blue one is the error after the synchronization phase, once we are synchronized. And when we exclude the synchronization time, the results show that the compensating tracking error is less than 2 centimeters for delays around 0.5 seconds, and about 2.5 centimeters delays around 1.5 seconds. So qualitatively, the user found the system difficult to use with a delay of more than 2 seconds, for which the error is about 3 centimeters after the transition and around 7 centimeters including the transition. So we have analyzed the general structure of a teleoperation system, and we presented some devices that can be used to teleoperate human robots. We've seen how to transfer the motion from the human to the robot, and how to obtain controllers that allow us to track efficiently the retargeting references. And finally, we've seen a technique that can be used to obtain a synchronized visual feedback when we have delays in the network. So what can be improved? Certainly, the inclusion of haptic feedback and auditory feedback can provide more situational awareness to the user, and more sense of presence in the context of existence. And the visual feedback can be improved. In our case, we use a first-person view from the robot's cameras, and in the last experiments, also a third-person view from an external camera. I think maybe both views should be combined, and if we use only the first-person view, certainly it has to be more stable to avoid motion sickness, especially when used with a virtual reality headset. So the next challenge is to extend the teleoperation to more complex scenarios closer to those encountered in the real world, which can be, for example, teleoperation. Local manipulation on uneven terrains in a bomb disposal or search and rescue operation. Clearly, in these situations, controlling simultaneously the upper body and the lower body of the robot is crucial. And it would be ideal if we could extend the whole body retargeting also to these kind of situations. However, it's not intuitive to extend whole body retargeting locomotions to whole body level. And the main constraint seems to be related to the setup at the user side, because working around is not possible. The user can't walk around, because of the limited workspace and because the environment at the user side is different than the environment at the robot side. So the user trying to control the robot might crash against some obstacles. And walking platform seems to make sense, but only for walking on flat ground. Furthermore, they constrain the upper body motion of the user. Whole body exoskeletons, as we see in these videos, could be a solution. However, if we walk around with them, still we have the same problem. So a solution that has been proposed is to fix the floating base of the exoskeleton, but this seems to generate natural user motions as we see in this video, and the dynamics information from the user motion loses its value. So probably this could work within the absence of gravity in space applications. Maybe an ideal solution would be to have a metamorphic walking platform that keeps the user at its center and rearranges its structure according to the next contact locations of the robot. This kind of platform doesn't exist, and although interesting, seems pretty complex to realize. So maybe using really high-level interfaces and simple interfaces like the joystick is the most simple, effective solution. And in this case, if this is the best solution to rely on a high-level interface, then it will take a long time and effort to teleoperate the robot, switching between full control of the robot during manipulation phases, and then switching to a high-level teleoperation mode to reposition the feet of the robot, and then switch back to full control of the robot. So an ideal improvement would be to autonomously let the robot to autonomously extend its workspace by repositioning its feet, while the robot, the user controls the robot during manipulation phases. And this will be an instance of share control. And other kinds of share control approaches could also be used to reduce the workload and effort of the user. For example, the ProMPs that we use for compensating for the delays could be used to guide the user in the task execution or to make the robot complete non-ergonomic tasks autonomously. So I'm curious to know your opinion about these possible improvements, and any kind of question, of course, is very welcome. And I thank you for the attention.
Okay, thank you very much for your talk. You were, I will say, perfect